Okay, we'll go ahead and get started. My name is Maiki. I am a senior application engineer here at nTopology. And today I will briefly show you how I was able to automate and parameterize the design of a heat exchanger to meet both performance requirements and do it in virtually any given design space, and hopefully inspire you to be able to create your own workflow similar to this, that can be automatically re-executed and iteratively designed to again meet performance requirements. To briefly describe the concept of this heat exchanger, we have hot fluid enter through the bottom right hand side, move through the heat exchanger and out the back left. Cold fluid enters through the back right hand side, comes through the heat exchanger and out the left. One thing that you might not be aware of is I used a TPMS or triply periodic minimal surface to create the heat exchanger core. And these structures are very unique and they allow a lot of surface area to be shared between the two fluid domains or regions, making them ideal for heat exchanger applications. Turning the attention to the model tree, I have it broken out into a handful of different sections. The first one being heat exchanger input parameters. As an engineer or a design engineer, the user can come in and update some of these parameters that are the performance requirements of your heat exchanger. So your total heat, the heat transfer coefficient, delta T, and so on, as well as the unit cell parameters. So you can define what type of lattice you'd like, the cell size, the thickness of that lattice, and all of these parameters are tied together so that when you change one, the design will automatically recalculate and update to continue meeting your requirements. And it's pretty simple. The way it's done is we calculate a target surface area that we want to meet, and then the workflow basically builds a volume for that and then starts to construct the heat exchanger core that you see in the center, as well as the ductwork on the left and right hand sides. So for example, let's assume that this heat exchanger is undersized. I could come here and let's just increase it to 32 kilowatts or 32,000, hit enter. And here in a moment as it renders, we'll see that the heat exchanger has grown a little bit to meet our current needs. As that's going, I'd also like to mention that we have a Q&A section, so feel free to ask any questions, and hopefully I'll be able to answer them throughout this demo process. But here we were able to see the heat exchanger grow just a bit here. I'm going to decrease the resolution so that it renders a bit quicker. And we'll just continue to kind of explore the workflow here. So how it essentially works is based on this target surface area, the user defines what type of lattice structure they want. So in this case, we chose a gyroid as our lattice structure. It looks at a unit cell, finds the area of this unit cell, and then figures out how many of these unit cells we need to meet our performance requirements. It then builds a design space or a heat exchanger infill volume that we're going to put our heat exchanger core in. And it initially is just this rectangular shape here. Now, the height of the ductwork is user defined, but this current setup is defined where the width and the length of the heat exchanger are predefined. So I can change here the height. Maybe we go down to 8 inches. The heat exchanger will shrink in height, but grow in width to still meet our performance requirements. It's pretty unique and amazing process how all of this can happen under the hood once you have the workflow set up. The next thing that gets controlled are the ducting thickness and basically the ducting parameters. So the distance between your left and right side ductwork, as well as the length of the ducting on either side of the heat exchanger here. Now, looking at that structure, you might be wondering how we keep the two fluids from mixing. Well, what we can do is we generate barriers or baffles that are used to keep those fluids from mixing. So looking inside here, we don't have those barriers on screen right now, but with a simple Boolean intersect, we're able to create baffles to keep those two fluids from mixing with one another. So again, let's presume that I'm going to hit I here just to isolate this view. Now let's presume that we've introduced some blowers to the inlet of both our hot and cold sections. So we're going to increase our heat transfer coefficient. Let's just double them almost. So we'll go to 200 for H2, and then we'll do the same thing for H1. And we'll see, since we've increased the heat transfer coefficient, the overall size of the heat exchanger is going to shrink and re-update. Yeah, so a general overview of the dimensions. Right now, I have this set, the height of the ductwork set at 8 inches, or about 200 millimeters. And then the width and length of the heat exchanger get calculated from there. And they're at about 600 millimeters. So about 3 times the width and the height, or sorry, 3 times the height there. So one unique feature that I added to this design process is a surface area comparison and refinement calculator. It's pretty simple how it works. I look at the percent difference between the target surface area that we are shooting for to meet our performance requirement, and compare it to the surface area of our final product here. And it's about 6% less than our target. The reason being is we've introduced the baffles, we have some blend radius, and we also cut off the corners here just to remove a little bit of stress concentration and improve the flow a little bit. So we're about 6% off of our target surface area. At the very bottom of the model tree, I created a little calculator that if I change this margin value here to what the calculator value is, it's tied into the rest of the design process. So if I hit enter, it's going to recalculate and redesign the heat exchanger and bring this percent difference of the target surface area to the final surface area of the heat exchanger a lot closer, so we're able to actually meet those performance requirements. So again, we've now dropped down to a 0.66% difference between the initial input parameters to what we have here on screen. And all that really did, it sounds fancy, but all we really did was change the infill volume that the heat exchanger is designed off of. So the size of the gyroid, right now I just have a unit cell size of 50 millimeters. I kept it constant in the X, Y, and Z axes. You are able to vary the cell size in either of the three directions, but in this particular case, I kept it uniform throughout. So that's a pretty quick rundown of this workflow, and really just kind of shows a lot of the capabilities that nTop platform offers a user in terms of reusability and being able to re-execute and design automatically to meet your needs. And this doesn't have to just be around heat exchangers. It can be structural requirements, thermal requirements, whatever you kind of desire, and whatever shapes you can throw at the software. We can pretty much handle whatever. So in this particular case, I'm going to answer some questions here. Are the two fluids mixed? I mentioned that I can keep them from mixing. So in this particular case, I kept them from mixing. You are able to have the two fluids mix if you'd like, but I introduced some baffles. So I'm going to turn these baffles on here. So with a simple Boolean intersect operation, we're able to create these baffles or flow diverters that keep the two fluids from mixing. So if I open up this ductwork here, we'll see that we have the hot fluid come in through this right. The blue on screen is the baffle used to keep the hot fluid from entering the cold domain of the gyroid heat exchanger. It moves through and comes out the right-hand side where we have this blue baffle or barrier again. And then the same thing happens with the cold fluid. It comes in, it's unable to enter the hot domain of the gyroid and exits out the far left-hand side. We are able to validate this in CFD. So you can actually go through, you can go to ntopology.com and go to support and find some blogs, extra documentation, and white papers showing another heat exchanger design where we actually took the fluid domains of a different heat exchanger. In that case, it was a fuel-cooled oil cooler. We mesh these fluid domains, bring them into ANSYS, and you can either run them in Fluent or CFX. Right now, I have the material of the heat exchanger set to aluminum. Definitely keep these questions coming in. So here's a question. When you link with CFD, how do you deal to define the interfaces for heat transfer between the fluids and the cooler structure? Can you define the interface element sets in nTop, or does it need to be done in ANSYS? We are able to define them in nTop. We are improving that workflow so that it's a bit more seamless when that happens. But you can either define them in nTop or in ANSYS as well. The current methodology or the methodology that I used for the fuel-cooled oil cooler example was to bring the domains into ISOM CFD and grab my interfaces that way. So whether that was the inlet or outlet boundary conditions or other interfaces. So what are the types of fluids that you cover? Liquid, gas, supercritical, etc. We are not a CFD platform or solver. So we don't really cover any of those. We play very nicely with external CAE tools. And so that's how we're able to validate any designs that we create in nTop here. Is the gyroid structure the optimum for this application, or would other TPMSs be better? That's a really good question. The two that I would say are probably best would either be the gyroid or the diamond TPMS structure. There's because additive is so new to everyone, and now that we're able to design and build these complex structures, there's a lot of studies that need to be done in order to figure out which structures are actually ideal for certain applications or whatnot. But again, we're able to quickly change the lattice type, so you're able to perform a DOE study, maybe on small sample units rather than such large or complex parts. But you can set up a DOE study to determine what lattice type is best. Have you tried linking nTopology to ANSYS Discovery Live for quick validation? I have, yes, and it works very well, primarily because we are able to export a nice clean STL from here, and then that gets turned into your voxel, or gets voxelized in Discovery Live, and you can run your quick validation study that way. Will this method be suitable for flow optimization and manifolds? I would think so, if I understand your question. Yes, we can bring in external data. So you can bring in a pressure field, let's say from ANSYS or whatever CAE tool you use, and we'll turn that into a field, and then you can create your geometry around that. So you would be able to, in that sense at least, optimize or design a manifold around that. Give it a couple more minutes for some additional questions, and then I'll go ahead and end this session. So here's a question. When I fixed the height, the width was automatically modified based on a constant volume size. Yes, that's correct. So the height is user defined, and then the length and the width get calculated based on that. So what ends up happening based on the target surface area that we are trying to hit, a volumetric infill gets created, and then the height that the user defines plays directly into that by calculating the width and the length. And that volume, this hex infill volume, is just simply defined by how many of these unit cells, these lattice unit cells, are required to hit this target surface area. What type of file can nTopology generate? So right now, I guess it depends on what you're trying to do and where you're trying to take that file. We can generate slice stacks if you want to go to manufacturing. We can export meshes if you're trying to go to a CAE tool. And here pretty soon we'll actually, depending on the complexity of your geometry, be able to generate step files as well to go into your into the rest of your design process. Can I show the library of different structured geometry available? Yeah, so here's a drop down of the different TPMS structures that you can play with. So gyroid, Schwartz, diamond, linonoid, split P, and Neovis. Give it just another minute or two, let a couple questions trickle in if they're going to, and then we'll go ahead and call it. I appreciate all of you who joined. I was pretty excited to share this workflow with you and expose just a handful of capabilities that nTop can offer. Cool. I'll go ahead and call it. Feel free to reach out to us at nTopology.com. You can find out a lot more information, request a demo, and lots of additional resources from there. Otherwise, stay tuned for additional nTop lives Monday, Wednesdays, and Fridays. Hope you all stay safe and healthy. Thank you for your time and attention.